All right, everybody. So you guys know some things are due. Hopefully, you guys have that turned in already. Hopefully, and here we go. Let me double check here. Let me get some things going on over here too. So I don't get any service here. So let me see if I can find it. No, this ain't gonna work for me. Okay. Anyway, I just have to deal with that. So my service here, my internet service in this basement jungle was not very good. So you know, so hopefully you guys aren't trying to turn things in this basement because if you are, you're gonna have an issue. You wanted to turn it in earlier. We'll see how that goes. Anyway, okay. Good morning to all of you guys. Sorry for the slight late start, but we're gonna talk about this next portion, which is related to sequences. It's very intimately related to sequences. Um, and that's called a series. And in fact, it's really an infinite series. So an infinite series, though, is AKA an infinite sum. Let's see, people having trouble finding the link. So here, just in case people are having trouble finding the link, let me copy it here. Okay, just in case. So here's that link in case people are having issues. And let me double check. Not everybody does. It's there. So I'm going to remind people. All right. Okay, so let's get this late start going here. Let's go to the iPad now. So late start. Okay. An infinite series, an infinite sum. And of course, you have this symbol here. If it's an infinite sum or any sum, you use capital sigma. That's the summation symbol. Okay, that's summation. That means to add. But then again, you might say, well, what in the world are we adding? Well, we're adding terms here. So if you remember, I want you guys to note you had a sequence. Here's essentially what this is, right? If you have a sequence, remember your notation was A1, A2, A3 forever now. That's your sequence. And then you might say, well, what are we doing now? Well, we're going to change those commas to a sum. So this is what you are looking at now. This is change this comma here. All these commas now get changed to a sum. And you say, well, what does that look like? Well, it looks like this. A1 plus A2 plus A3. So you change the comma to a sum, and now we are adding these terms, and notation-wise, we say n is 1 to infinity. So there's a notation. A1 plus A2 plus A3, and that goes on forever. Okay, and I guess I was using the wrong color. This is your infinite sum, ladies and gentlemen. Okay, so you might say, okay, now what do we care about with these here? What is it that we really care? So I want you guys to know we care about really two things. It's really one thing. Either now, what we're going to talk about here is this. Either the series converges or what? Or diverges. Okay. Now this is going to have to, we're going to have some discussion here on this. Either this particular series converge or diverge. Now you say, Mr. Judge, that doesn't make any sense. Okay, it will make sense when we start to give you more information here, right? So I want you guys to note here. Here's the thing. Either this thing adds up to some finite value L. L is finite. Or it's infinite. That's really what we're talking about. And this is where the series will converge. We say here the series converges. Or the series will diverge. And so now we're going to have to just simply dive deep into what this means here to converge or diverge. Because you might say, how in the world can a series converge? Where's the limit? You guys know what I'm saying? Where's the limit here for a series to converge? All right, what do you mean the series diverge? Where is the limit? Well, it's related to 12.1. It is related to sequences. So we have to define a series in terms of what we call, we're going to consider what is known as the sequence of partial sums. So we're going to consider a sequence of what we call partial sums. And then all of these definitions here are going to make sense to us. Okay, if we consider the sequence of partial sums, now you might say, what is that? So you're going to have to define for you here a sequence of partial sums. Okay, so that it'll make sense. Now remember this. This is the definition of what we call a sequence of partial sums. Sn is defined to be A1 plus A2 all the way up to AN. So this is really the sum of the first M terms. Okay? Now you might say, well, what do you mean? What does that mean? This is how we define. So notice this N here. This is the key. N goes from 1 up to what? To little n. Sequence of partial sums. And so here's kind of what we mean by that. So if you said, okay, what is S1? Well, S1 is just simply that first term, A1. S2 is A1 plus A2. Okay, you guys see what we're saying? So notice the N value here, right? That's what I'm saying. S3 is A1 plus A2 plus A3. So All right, you guys okay with that? That's what they're calling the sequence of partial sums, meaning add the first n terms. So S1 is A1, S2 is A1 plus A2. It's the sum of the first two terms. S3 is the sum of the first three terms. You say, what is S4? Well, add the first four terms. And we go down to, this is kind of what they would like you guys to know. You can say SK is the sum of the first K terms. Okay? This sequence of partial sums. So K, start at 1, go to 2, end at K. So, in other words, this is what you can do. I mean, we can write it a couple of ways. We can write it this way that well, yeah, how do we're going to say there SK is the sum from K starts from 1 well to N, or I should say SN, so you guys know, of this AK, if you want to look at it that way. And what you obtain is this sequence S1, S2, S3, really up to S, whatever you want, SK, SN, doesn't matter. This is going to go on forever. Okay, this is going to be that infinite sequence here. This is called the sequence of partial sums, right up here. So this is just notation now. You start when K is 1. And this is your index, K, and you end at N. That's the sequence of partial sums, your first N terms. Now that creates this sequence here, this infinite sequence, because we want to know, we want to look at this here as N goes to infinity. The sequence of partial sums as N goes to infinity. This is what you're seeing. This is why we say, let N keep going forever. And that's why we can talk about whether this converges or diverges, because you're really talking about the sequence of partial sums. Okay, so the question is going to be essentially that. That's the big question. The sequence of partial sums will either converge or diverge. And that's how you get the infinite sum. All right, so just kind of let you guys know, this is kind of the big deal, right? So, all right, let me see if I can give people, yeah, here we go. Okay, definition. We say the infinite series now converges to, let's say, sum L, whatever. Their book says sum S. So maybe I'll just do that. S is the sum. Okay? If the sequence of partial sums now, that limit, N goes to infinity of Sn equals S. S is that finite number. So I'm going to color this purple, I guess, or something. I don't know. It doesn't matter. Blue. This is finite. Okay? And that's kind of really what you care about. This definition is the theoretical definition that we talk about for now a series converging or diverging. It's really saying the series adds up to that sum. Okay? This sequence of partial sums, as n goes to infinity now, is finite. So that's the essence of what we're talking about here. This is our sequence of partial sums. And whether the series, the book called that S, I called it L. We can change it to S. That's fine. And that's the essence of what we're now transitioning to. We now have an infinite sum, an infinite series. Add the terms. Does the sequence of partial sums converge to a finite value L? If so, we say the series converges. Okay? And this is all about that series here. So that means that this sum, this is what this means. N goes from 1 to infinity. That's exactly what they're talking about. And let me move it down. Okay, that's the essence of what we're doing now. We're transitioning now to an infinite series. That series will converge to a finite value if the sequence of partial sums converges to a finite value. If it diverges, well, then it diverges. And that's what we mean about a series. Now, this is all a very theoretical result. Let me just say this to you guys. This is all theoretical in theory. Okay? Because generally speaking, it is very, very difficult for you to show that a sequence of partial sums converges. Generally speaking. All right, I'm going to say that again. Generally speaking, hard to use this definition. But in the beginning, they give you some kinds of series that you can use. So I'm going to emphasize that again. In the beginning here, there are going to be some series where we can use this definition. But as we proceed, very difficult to use this definition. You have, there's more math under the hood, and then you have various tests that we'll have, and that's what we'll go with. But I just want to start off that in the beginning, as an example, they'll give you one of the most very simple examples you can see. And very simple, something like, for example, show that this particular series converges. Okay, so they want you to show that this series converges. So in the beginning, and you might say this is what you say. You say, consider the sequence of partial sums. So they're essentially going to use that definition here when you create that sequence of partial sums. They're going to use this. But generally speaking, very hard to do. So, okay. Now you might say, well, what does this mean? Well, S1 is A1, which is just really 1. N is 1. That's just really 1/2, just so you guys can see every detail. Right? Because we're now going to say, okay, we're going to add those terms now. And this is the AN that we're talking about, right? So here's my AN. S2 is A1 plus A2, which is 1 over 2 to the first power, plus 1 over 2 to the second power. S3, A1 plus A2 plus A3, 1 over 2 to the first power, 1 over 2 to the second power, plus 1 over 2 to the third power. Okay, you guys see the point? Now you say, what's the nth? This is what you want to get to. What is this? What is the nth term? We want to get to the nth term, and you say, well, what is that? That's 1 over 2 to the first power plus 1 over 2 squared, 1 over 2 cubed, and that goes all the way to 1 over 2 to the what? Nth power. Oops, let me try to, I'm going to highlight this here. Okay, you guys okay with that? And you go, oh, that's Sn. So in theory, here's again the theory part, right? You say, Mr. Judge, I have to take that limit as n goes to infinity Sn. And you tell me, is that going to be the limit, again, n goes to infinity of, what's this? 1 over 2, 1 over 2 squared, 1 over 2 to the nth power. And we have to find if this limit converges. You guys with me on that? Now, here's the thing about this. Okay? There's a little bit extra work here. This is what's going on here. There's more. We're going to approach this differently. Okay? So I want you guys to know what we know so far. We have Sn, which is 1/2, 1 over 2 squared, 1 over 2 to the n. And I'm going to do this. I'm going to take 1/2, or no, let's do this here. Yeah, we can do that. Let's get the next term, right? If I said to you guys, what is this? S to the n plus 1. That's the next term. That's 1/2 plus 1 over 2 squared, all the way up to 1 over 2 to the n, 1 over 2 to the n plus 1. Okay, so I just want you to know there's a process here now. Okay. Now, here's what I'm going to do here. No, let me say, what are we going to do now with this? I want you guys to notice this is going to equal this portion right here. Just so you guys know, we called, I think we have to change that color. Okay, just want you guys just to kind of note, that's Sn plus 1 over what? 2 plus 1. Okay, so far so good. You guys okay with that? Okay. Now I'm going to do some algebra here. Let me show you guys. What is 1/2 Sn? 1/2 Sn. Sn was 1/2 plus 1 over 2 squared, all the way up to 1 over 2 to the nth power here. And that's going to be 1 over 2 squared plus 1 over 2 cubed, all the way up to 1 over 2 n plus 1. Okay, this is 1/2 Sn. So you might say, okay, where are we going with this? Well, we're going to take this difference here, I think. Where is this here? Yeah, I'm going to take this difference. Notice this. We're going to take the difference now. We're going to take Sn minus 1/2 Sn. Okay, so Sn minus 1/2 Sn. So what is Sn again? The numerator is, this is going to be the 1/2 plus 1 over 2 squared. That goes all the way up to 1 over 2 to the nth power now. And then 1/2 Sn, we already figured out what that is. That's right here. It's 1/2 squared plus 1 over 2 cubed plus 1 over 2 to the n plus 1 over 2 to the n plus 1 now. So I want you guys to see what I'm doing here. Let's color coordinate this here. This is orange, okay? And then this is green here. Now, if we take this difference, notice what this gives us. This gives us 1/2 plus 1 over 2 squared. 1 over 2 to the n minus 1 over 2 squared minus 1 over 2 cubed all the way up to minus 1 over 2 to the n minus 1 over 2 to the n plus 1. So everything in orange is right here, and everything in green is right here. So what is that difference? You say that difference is going to be, everything here is going to collapse here. Okay, all the positives and negatives collapse. This is called collapsing. And then what you're left with really is the following here. Okay, we're left with one half minus 1 over 2 to the n plus 1. That's on the right side. But on the left side, you said don't forget what you started with. On the left, this portion up here, right? That's going to give us 1/2 Sn. So 1 minus 1/2 Sn, that's going to be what you get. Now, multiply both sides by 2. And we get 1 minus 2 to the n plus 1, which is 1 minus 1 over, this is what we end up with, algebraically speaking. So I'm able to get a nice closed formula for Sn. Okay, this is what's called a closed formula here. It's not an infinite sum. Like, remember Sn, what I'm showing you guys here is Sn, this is Sn. That's I'm like, take it back, a finite sum. This is finite. Okay, this is a finite sum. Now we have it written this way, and that's the whole idea. Because now we can take the limit now. You say, what's the limit? So the limit, n goes to infinity, of Sn is the limit, n goes to infinity, of 1 minus 1 over 2 to the n. And that is 1. Okay? So what did we just show? Here's what we showed. Sn goes to 1. That's finite as n goes to infinity. This is the essence of what you guys want to show, that the sequence of partial sums converges to a finite value 1. And so that particular sum now that you're looking at, the sum of 1 over 2 to the n, okay, excuse me, is 1. And it goes to 1 to infinity. So the reason you had to go through sequences and find out whether these sequences converge or diverge is because of what you're looking at right now. Okay, we say here, this is what we say. The series converges as the sequence of partial sums converge. That sum is 1. Okay, that's the AN there. So that's the difference now between a sequence and a series. Now we're adding the terms forever, and we're trying to see if the sequence of partial sums converge. If it does, the series converges. If it doesn't, the series diverges. And it comes from this theoretical result. Like I said in the beginning here, they give us some series that can converge or diverge that you can show by the definition using sequence of partial sums. That is the key in the beginning, but that's not always the case. As we proceed in the course, that's going to all be very much easier said than what? Than done. Now, what I just did, in all honesty, ladies and gentlemen, I'm going to give you guys an important tool here. Does anybody know what kind of series this is? It's a very special series. Okay, because we're going to start to study these kind of series here. Very special. What I shared with you guys here is a geometric series. So I'm going to give you guys a definition here to start today about geometric series. Any series that looks like this. So this is what they give you guys. Geometric series is anything that looks like this. A r to the n minus 1, where n is 1 to infinity. Now, what this looks like is the following here. AR squared, and that goes on forever. So one of the first series that you guys study is called the geometric series. That's the definition. Okay? So here's what I'm going to give you guys. Here's a fact here. And this is what we're going to show about geometric series. Okay, here's a big fact. The geometric series will converge to a finite value r. This is finite. It does converge, but what does it converge for? That's only what? If the absolute value of r is less than 1. Okay, so this is the very famous geometric series convergence. Yes? And that's because if you put 1 in r, it's going to equal 0. No. R is going to be any value of r. Here's what they mean by that. And I'm going to prove it to you. R has to be between -1 and 1. Okay, if r is between -1 and 1, the geometric series will converge. I'll share with you guys why that is. I'm going to prove it to you guys. But this is our first, series. This is like a series test, if you want to think of it that way. right? So this is like an important test. So what's going to happen in this section is you're going to get a whole bunch of tests about whether a series converge or diverge. Geometric series. So you say, what's the proof? I'll share with you guys the proof here, right? This is, like I said, you said, oh my God, what is this, Mr. Judge? This is the test. If the absolute value of R is smaller than 1, then we have convergence. We even know what it converges to. A over 1 minus R. Okay, so let's give you guys this proof. We gave you guys this fact. This is the test. So we're going to say this. Here's the proof. Okay. Consider the sequence of partial sums. I essentially did a particular case with this prior example. So here's how we do that. The sequence of partial sums, remember that's S1, S2, S3, and so on. It's an infinite sequence. We got to look at that sequence, right? So you might say, well, what is that sequence again? Well, remember, what is Sn? It's A1 plus A2 all the way up to An by definition. Okay? That's the nth term. Now, what is this particular sequence, right? So here's the sequence right in here. So if I said, can you write this down? Yeah, what this looks like for us is going to be this. A, because what happens, remember, what happens when n is 1 here, right? If n is 1, isn't that r to the, let's write out every term. That's a to the r to the 1 minus 1 plus a to the r 2 minus 1 all the way up to a to the r n minus 1, I believe. Right? Because this is how you define it. Change your n value. Start with 1, go to 2 and 3 and 4 and so on. So you end up with a to the r to the 0 plus a to the r to the first a to the r to the n minus 1. And that's just going to be a plus ar all the way up to ar n minus 1. Because your an is an ar to the n minus 1. Okay? You're using this right there. There's your an. All right. Okay, what's the deal now? Here's your Sn. Now what you guys do is exactly what we did before. I'm going to take R, multiply it to Sn. So R gets multiplied to all this again. AR squared all the way up to AR to the N. Okay, that's my R Sn. So we're just using the definition there. And then a little bit of algebra. Now, what I'm going to do here again is I'm going to take now Sn minus R to the Sn. So I'm going to use my colors again. Share with you guys this. This is your definition of Sn, sequence of partial sums. And this is that R Sn over here. Okay, so, here's the R. So here we go. So the first term is A plus AR to the n minus 1. Now that's minus now. AR plus AR squared plus all the way up to AR. which gives you the following here. A plus AR up to AR to the n minus 1. That's the orange portion. Okay, so I'm going to have to do the orange portion here. And then minus that green portion. So all I did was the orange. Now we have to do subtracting the green by algebra. Right? So it's minus AR, because we're going to distribute that negative sign. Of course, minus AR squared, all the way up to, there is the prior term, AR n minus 1, and then AR. And that's to the n. I apologize, I left the n off. So this is going to be that green portion now. Right? This is a classic proof in every calculus book of your geometric series. Now, on the left side here, so you guys can see that here, on the left, you can think of that maybe as factor out your Sn. So you have 1 minus r with the Sn. And then what happens on the right side is all the collapsing here. And then you get this A minus AR to the n. There's the collapsing portion. That collapse, that's going to collapse. So I can now solve for Sn, and you say, okay, I get A minus ARN over 1 minus R. Just solving for the Sn. Now we get this closed form again. Right? You go, nice. You got a closed form for Sn. For now we can take the what? We could take the limit of this. So you might say, well, how do we take the limit now? Well, let me remark about this. I think what you can do, and sometimes people do, is they'll factor out the A, and you left 1 minus R to the n here. And bring that 1 minus r. Now, notice this. This is what some people do with the algebra. All of these things are constants. So you get Sn going to be A over, factor out the constants. Now you have 1 minus r to the n. And that's a closed form that you want to take the limit for. All right? So now you say, okay, what's the limit? Sn. A, 1 minus r. Okay, don't forget, what is this? All of these values are constants. I can pull that out. I can pull out my constant. Now, who remembers the other day? What did I say with you guys the other day here? Remember this? By properties of limits, what do you guys remember? We proved something like this here. R to the n goes to 0 when what happens? What do you guys know about R? Yes, absolute value of R is less than what? 1. So that's what we say. That whole thing, this goes to 0. That was with a sequence. We already seen that. R to the n goes to 0 when the absolute value of R is less than 1. So that's your key criteria for convergence now. Because 1 minus 0 is 0. And now we can say this equals what? A over 1 minus R. So what we just showed is very big. You say, what do you mean? Sn, the sequence of partial sums, goes to the constant A over 1 minus R when the absolute value of R is less than 1. This is convergent. This is that sequence of partial sums. So, you know, this is, of course, as n gets big. So that's the finite value we're looking for. And remember, it diverges for other values of r. We've seen that already. So, ladies and gentlemen, it goes back to using that key fact. So this is why you have to know about that fact. This is why you guys have to know about the convergence of sequences. So what we showed is that sequence of partial sums converges, and this is what we proved here. Okay, for the geometric series, we proved this fact. And that's important. Now that's your first test, in all honesty, about a series converging. That's the very, very, very first test. So, ladies and gentlemen, it's like, welcome to the what? Welcome to sort of series where you get to look at the sequence of partial sums now, converging. All right, so let's give you guys an example, because you go, I have no idea what this looks like, as an example, right? What are some examples of this situation? All right, let me give you another example, maybe a quick and easy example. Let's look at some examples, right? So if you said, what if they gave me 1 over 3 to the n, n goes to 1 to infinity, I guess. Let me go back. I want to be careful here. I want to give you guys exactly how that looks. All right, n is 1. I'm going to say 1/3 to the n minus 1, okay? Okay, now remember, what is this supposed to be here? So let me kind of remark here about this here. This is my an. You guys okay with that? So what you want to know is this. Here's the first step. Is this sequence geometric? So here's your first test. Is your sequence geometric? How do you guys think you can prove that that's geometric? I'm just kind of curious. Right? Look at the terms. Here's what you guys do. You say, okay, here's 1/3 to the n minus 1. N goes from 1 to infinity. What do the terms look like? 1/3 n is 1. 1 minus 1 plus 1/3 what? 2 minus 1 plus 1/3 3 minus 1. And that's supposed to go on forever. Is that right? By definition of the series? Because now your index here, n is 1. You change that. N goes from 1, 2, 3, 4, 5, 6, and so on. So you're going to have to check, and that's 1/3 now to what power? 0. Plus 1/3 to the 1. Plus 1/3 squared, and then that goes on forever. 1 plus 1/3 plus 1 over 3 to the second power. Really 1/9, but okay. And then that pattern goes on forever, okay? So then we're trying to answer, is this geometric? Okay, this is the process you got to go through. Is it geometric? And what do you guys know? If it were geometric, this is A plus AR plus AR squared, and it would continue that pattern forever, okay? Because the definition of a geometric series is right up here. Okay, it has to have that pattern here. AR squared plus A plus AR plus AR squared and so on. So it's going to have that pattern. So here's what you guys do. You're going to have to do this. You're going to say, okay, if A is 1, that's the first term, AR is supposed to be 1/3. You guys okay with that? Because you're looking at the terms. What that means here is that AR to the second power better be what? Put the value here. This is what you guys want to do. Use A as 1. There's my A. R is 1/3 then. So you test it. Is AR squared 1 times what? 1/3 squared? Right? If you plug in the values for A and R, here's my R value. So this becomes 1/3 to the second power. So is it true? If A is 1, AR is 1/3, is AR squared 1/3 squared? The answer is yes. You know what that means? It's geometric. So these terms here, right in here, are geometric. Well, that's good. Because I know I have convergence if what? If the absolute value of R, which equals absolute value, what is R? Okay, what is R? Uh-oh, I have to find R, ladies and gentlemen. A is 1. So that's 1 times R equals 1/3. Isn't A 1? You say A is 1 here. So R is going to be what number? 1/3? Absolute value of 1/3 is what? 1/3. Is that smaller than 1? So yeah. So guess what, ladies and gentlemen? Our R value of 1/3 is smaller than 1. So this is a convergent what? Geometric series. So I can say to you guys that this thing is what? It's a convergent series. The sequence of partial sums converge. I don't have to do all that work. I just showed you guys because I proved in general what this is. Now, they might ask you this question. What's the sum then if it converges and it's geometric? Well, your sum is right here. Where was it? I think we proved it. Well, it's in the statement. We did prove it. This, ladies and gentlemen, is the what? That's the sum for a convergent geometric series. You need to know what A is, and you need to know what R is. If you know what those two things are, what do you get? The sum. Well, you do know what those are. A over 1 minus R, right? You say, we know the sum A over 1 minus R. What is A here? 1. What is R? 1/3. So that sum is found by doing this arithmetic. So, okay, you're going to have to do some what? Subtraction here. 1 over 2/3. That's 1 divided by what? 2/3, which is in fact 3/2. Ladies and gentlemen, you're done. That sum here, what we've shown is this. 1/3, and I think they gave it to the nth power. That's 3/2. And this is all about the sequence of partial sums converging. And converges to 3/2. Now, I just want to remark here for you guys. This is a very, very important remark here. This is a very, very important section that we just started. There's a lot of work in this section, 12.2 as well, just like 12.1. And what I do here in 12.2 is like what you guys seen we did here today, which is show people here what the definition of a series is. It's really an infinite series. Show what it means by definition to converge, a series to converge. It's a sequence of partial sums converging. It's a finite number. and then show you that the geometric series converges with the absolute value of r being smaller than 1, and then give you some examples of geometric series and the convergence. This is known as a test. It's your first test. All of chapter 12, as it relates to series, you're going to see in like the next, I don't know, 5 or 6 sections, various tests for convergence. So you have to know this is one test for convergence, only one. This is only the start of that section 12.2. It's long as well. So we're going to see a whole bunch of tests for convergence. This is your first one. This is known as geometric series, the geometric series test, in all honesty. The absolute value of r has to be geometric. The absolute value of r has to be what? Smaller than 1. Okay, you guys okay with that? What do you guys think? I know it's only your first example, and I know you just started, but you're going to see more and more of these, and we're going to see more tests, different kinds of series, and different tests for convergence. And every test is based on the kind of series that you actually see. And so this is the start of our series work. And let's look at the assignment portion for now. Because I'll be going over some more. But this is actually 12.2. So 12.1 was we did a lot of stuff. This is on sequences. 12.2 is series. We just started it. So what I'm going to say today, what you might want to do today is read 12.2. Because we're going to continue tomorrow with some more 12.2 series. We just started that. All right, you guys okay with that? I know it's only a few couple of examples, but every calculus book goes through exactly what I just talked about today. I might even use the same examples. You can start with 1/2 to the n, or 1/2 to the n power, which is 1/2 to the n power, or do 1/3 to the n power. Essentially, what you're going to see is you just have to find r. And like something like this, just so you guys know, just as a note, n is 1 to infinity, just a note here. Yeah, let's get that. Okay. And that's n minus 1. So the terms here, this is an would be 3/2 n minus 1. This will be geometric, just so you guys know. I'm just going to give you guys a note. So you can verify this is geometric. R here is going to be 3/2. And the problem is that the absolute value of r is 3/2. And that is not, ladies and gentlemen, this thing here is not smaller than 1. So if you said, what do I do with this? What does that mean? Well, that means the series what? Diverges. What it really means is a sequence of partial sums diverge. It means that you can't add up the values forever and it be finite. It explodes. It gets too big. The sum is too big. It's not a finite number. So what that'll mean, I mean, just so you guys know, this is just how to use that geometric series test that I proved to you guys. That's going to be just how simple that is. But you have to verify that this is geometric. So if you have a geometric series, you get to use that test. If you don't, you can't use it. So that's what we'll start to discuss tomorrow. All right, you guys okay with that? This is your dive into the work of sequence and series. And good morning to all you guys at home. We had about 12 or 13 people at home, and now it's down to 11. But anyway, okay, you guys, you can read that. We'll continue tomorrow, and stay safe and have a wonderful day. There we go. Now, remember, all I shared with you guys last time, well, I shouldn't say all. We talked about a lot of things. What a series is, what does it mean for a series to converge? The sequence of finite sums converges. And it adds up to that sum S. And then we introduce you guys a geometric series here. and shared with you guys the conditions in which the geometric series converge. Now, I'll give you guys another example of this. Some more examples of this geometric series situation so you guys can see that. Okay, so here's kind of another example. They can write it this way for you guys. They can say, here you go. Here's a sum, 1/8, 1/4, plus 1/2, minus 1, plus. And so they're going to say, determine if the geometric series converge. Okay. Okay. And so I'm going to have you guys try this out a little bit. Okay, so notice this. Here's what I want you guys to know. You have to verify that this is geometric. In other words, this is A, this is AR, this is AR squared. This would be AR cubed. Because remember how they define this? They define this as the following. AR n minus 1, which is A plus AR plus AR squared. And again, that converges. In other words, that sum is A over 1 minus R. And here's what you guys want to remember. If the absolute value of R is smaller than 1. So I'm going to ask you guys to take a few minutes yourself to verify that this thing is what? Is geometric. And let's see what you guys get. Okay, just take a few seconds on that. All right. What'd you guys get? Anybody get anything? Well, does it diverge or does it converge? Right? Remember, how do you do this? You're going to say A equals, if we can get this out, come on. Yeah. A equals what? 1/8. Is that right? What does AR equal? Minus 1/4. Do you guys see that there? You're looking at the first two terms. Is that right? So if you're looking at this first two terms, how do we put this together? What does this imply? That implies that AR being negative 1/4 when A is, what's this? 1/8. You have the equation 1/8 R is negative 1/4. What is R then? It's negative 1/4 divided by 1/8, bless you. R is going to 1/4 times 8, or R is going to be what? Negative 2. Now, I don't know that this is geometric. Okay, how do I verify that this is actually geometric, though? Right? Is this geometric? Go back where? Right here. If this is geometric, AR squared better be 1/2. Do you guys agree with that? So how you verify this is geometric is you say AR squared needs to be 1/2. Well, let's see if that's true. Okay. So we get A, 1/8 for A. R is negative 2. Does this equal 1/2? What do you guys think? What's this going to be? 1/8 times 4 is in fact 1/2. So guess what, ladies and gentlemen? This is in fact geometric. So the absolute value of R in this case is the absolute value of negative 2, which is positive 2, and that's bigger than 1. And we want you guys to be able to see this. This means there's a problem. Is that right? In order to have convergence, what's the deal? That R needs to be smaller, an absolute value needs to be smaller than 1. So therefore, this is a divergent geometric series. This is divergent. Okay, there you guys go. Yeah. First three terms. Yeah, it's enough. It's enough. In all honesty, yeah. Anyway, so there you guys go. This is another example of geometric, you know. And then you might say, what if they give it to you something like this? 1 plus 0.4 plus 0.16 plus 0.064. Again, what's the deal here? You got what? AR squared, AR cubed. So this means A is 1, AR is 0.4. Okay? So you're going to repeat this process here. Since A is 1, replace this A with 1. What does that mean R has to be? 0.4. Okay? So what you check now is really right in here, AR squared. So verify that. AR squared is 1 times 0.4 to the second power. That better be 0.162. And is that true? The answer is what? Yes. So because that's true, what do you guys know? This is going to be what? Geometric. So the absolute value of R now is the absolute value of 0.4. That equals 0.4. Is that less than 1? So what do you guys know? You have convergence. So since this is geometric and it converges, what does it converge to? Well, we have to have A over 1 minus R, right? So we plug in the values. A is 1, and then 1 minus 0.4. That's what our sum's going to be. So it's 1 over 0.6, which is 1 over 6/10, which is going to be 10 over 6. So that sum reduces to, looks like it's 5/3. So double check my algebra, ladies and gentlemen, or my arithmetic. But you guys have the sum. That's 5/3. So this whole thing adds up to 5/3. Okay, all these terms, when you add them, they equal what? 5/3. That's the nice thing about the geometric series. You can actually not only know if it converges, you actually know the sum. Okay, what do you guys, is that okay? What do you guys think? Is that a pretty good question? We'll say that again? No, that's the sum of the value. That's the infinite sum. You know, and then they have questions that look like this. You say, Mr. Judge, what if they give me something like this here? Okay, so let's look at this. Let's look at the terms of the series here. If n is 1, I guess I'll have to write it down this way. 1 minus 1. I'll just write it down this way. Okay, now n is 2. Now n is 3. Okay, do that there. So this looks like this is 1. Is that true? Plus negative 6/5. Plus negative 6/5 to the second power here. Okay, now adding a negative just means subtraction here. So go through the same process. This is A, this is AR, this is AR squared here. So let's check to see if this is geometric. A is 1, AR is negative 6 to the 5th power. So all together now, using a little bit of algebra, plug in A is 1. That means R is what? Negative 6/5. Okay, what do I have to check to see if this is geometric again? You have to do what? Yeah, AR squared. So AR squared becomes 1 times negative 6/5 squared. And isn't that negative 6/5 squared? Isn't that AR squared? So we have a geometric series. Is that true? Now, what do you have to have for convergence here? What's the test? The test is that the absolute value of R is going to be the absolute value of negative 6 to the 5th power, which is 6 to the 5th power. And that is not, ladies and gentlemen, smaller than 1. Is that true? So then what does that mean about the series? Diverges. Yeah, it's divergent. Is that easy peasy lemon squeezy? Sum. 0 to infinity. 1 over the square root of 2 to the nth power. And notice this here. Notice where you start in this one. You start at 0. So you can start at 0. That means I have 1 over square root of 2 to the 0. 1 over square root of 2 to the 1. 1 over square root of 2 squared, and then that goes on forever. Which is 1 plus 1 over the square root of 2. Write it this way. AR squared. A is 1. AR is 1 over the square root of 2. Is that right? So what does that mean about R then altogether? Plug in a 1 here, and that means R is 1 over the square root of 2. Okay. Let's verify the next term now, AR squared. You got to verify that. So if this is geometric again, what do we know? AR squared should be what? 1 times 1 over the square root of 2 squared, which will be 1 over the square root of 2 squared. So what did we just show? That this is another what? This is a geometric series. Now, why is that important to do? Well, because then the absolute value of R, which is the absolute value of 1 over the square root of 2, which is 1 over the square root of 2. What do you guys know? Is that number, is that bigger than 1 or smaller than 1? That's smaller than 1? Then what does that mean? That means the series converges. And what's the sum? You got to use the sum formula. S is A over 1 minus R for the sum. So you're going to say now what? What is A? 1. And then 1 minus 1. So then we're going to have to do a little bit of algebra, right? You guys know what I'm talking about? Square root of 2, square root of 2, minus 1 over the square root of 2. Square root of 2 minus 1 over the square root of 2. You guys know what this becomes? This is going to be what? 1 divided by the square root of 2 minus 1 over the square root of 2. 1 times the square root of 2 over the square root of 2 minus 1. So my sum is the square root of 2 over square root of 2 minus 1. There you go. And then, ladies and gentlemen, they can do something like this. They can say 0.35 right? 0.35 as a fraction, right? So what is this? 0.35 is going to be what? Nope. Isn't that the meaning with that line that's on top? You guys know what I'm saying? You say, write this thing as a fraction. Okay, now, that's 0.35 plus 0.0035. Is that true? And then that pattern goes on forever. Now there's going to be 4 zeros. 1, 2, 3, 4, 3, 5, and that will continue forever. Okay, because this is the meaning of this. This is what? Terminating. This pattern goes on forever. Non-terminating. So write this as a fraction now. What's 0.35? Isn't that going to be what? 35 over 100? And what's this? 35 over 100 squared. 35 over 100 cubed, by the way. Okay, and that pattern is going to repeat forever. So the question I'm going to ask you guys is, note, I'm going to make this observation that this is a geometric series. Okay, so this is a geometric series. AR squared. How do I know for certain that this is geometric? Do you guys know how we know? We have to prove it. Say, how do you prove it? Well, we have to kind of show that. So A is going to be 35 over 100. AR is going to be 35 over 100 squared. So what does that mean about your R again, right? That means 35 over 100 times R has to be 35 over 100 squared. What do you think that means R has to be? What is R? Is that 1 over 100? Okay. So believe it or not, this is going to be another geometric series. You say, how do I know? We're going to have to verify the next term, just like before. So you can verify AR squared. Now, how do we verify AR squared? It's 35 over 100 times 1 over 100 squared needs to equal what? 35 over 100 to the what power? Third power. Is that right? You guys see what I say? 35 over 100 to the third power? So this is 35 over 100 times 1 over 100 to the second power. And sure enough, doesn't that equal 35 over 100 to the third power? So, ladies and gentlemen, this is in fact what? This is a geometric series. So if this is geometric, what's the story? When do you have convergence? If the absolute value of R, which is the absolute value of 1 over 100, which is 1 over 100, isn't that less than 1? So in other words, this has a finite sum here. What is it? A over 1 minus R. Okay? So what is that sum, though? Yeah, let's write this down. This is going to be here 35 over 100 over 1 minus 1 over 100, because what was A? Go back over here. This is my A value. Is that right? Isn't that A? So A goes right here. 1 minus what? R. This is R value. So do a little bit of arithmetic. You say, what's my arithmetic? This is 100 over what? 100. So we get 35 over 100 divided by really 99 over 100. And that's going to be what? 35 over 99. So let's write down what this means here. What did you just find? That this sum here is 35 over what? 99. So these non-terminating decimals are in fact fractions. So if I go to the TI now, and if I say to you, can we see this in the TI? Yes, we can. Let's clear this out. What's this going to be? 35 divided by 99. What do you guys get? Okay, that's your fraction, 35 over 99, written as a non-terminating decimal, meaning it never stops. And there's a pattern, 35, 35, 35, 35 forever. That means this non-terminating decimal is a rational number. It's a fraction. And so this is kind of a lesson in demonstrating that these numbers are in fact fractions. But they're geometric, they're geometric series. It's kind of like writing down, for example, if you said to me, a very simple one, if I said to you, what about this example? Right? What is this? What's 0.3 with that line on top? Isn't that going to be what? Isn't this what this is by definition? We're going to want to write this as a fraction as well. So, some of the homework says write as a what? Fraction. And this is a non-terminating decimal. Non-terminating, never ends. That's what non-terminating means. So, write this, what's going on here? Write this as a sum. As an infinite sum, because that's what it is. You're looking at an infinite sum. Right? Because you're saying, what's terminating right here? I'm sorry, what's repeating? What's repeating is that 3 forever. So this is going to be geometric. You might say, how do I know this is geometric? Well, because let's demonstrate it. Let's do what we've been doing here. These 3 terms. A is 0.3.
To do that, you'll need to be online.
Sorry, Siri. I don't know what I touched.
To do that.
Get rid of Siri. Goodbye, Siri.
To do that, you'll need to be online.
Siri, can you go away? How do you guys get rid of Siri?
To do that, you'll need to be online.
I want to get rid of Siri. I have to what? I got to go to settings now? Settings. I have to look for what? Oh.
On the accessibility one. On the left?
On the left.
There's underneath the notification, the Siri, click that. And then look for the accessibility to take it off. You can turn off Face Siri too. So that way, like, if anything that sounds like Siri doesn't show up.
Goodbye, Siri. Anyway, thank you so much. What happens is you become such an old man, you don't even know how technology works. I used to be a technology guru too. Not anymore. What happens is things change so fast and they don't necessarily change logically. So now things are like very illogical. At least that's how I see it, but maybe people disagree. maybe if you're young, you disagree, right? You might say, no, things were pretty good. Like, what kind of happens now is even your Apple TV is confusing. At least I think it is. What's our R? Isn't that 0.3 over... You guys know what I'm saying? What's R have to be? Do you guys know? Is that 3 over 100 divided by 3 over what? 10? What's R? Isn't R 1/10? So R is, R was 1/10, which is actually 0.1, okay? So I got the R value. So we just have to verify the next term. AR squared. What is that AR squared? Let's do that here. That's going to be, AR squared will be 0.3. We just found R to be, what is that? 1/10. We have to square that. 0.3, it's 1 over 2 squared. Well, that's 3/10. 1 over 10 to the second power. That becomes 3 over 10 to the third power. Is that right? Is that what this is? It looks like 0.12 what? 3. And that's what you guys see here. So sure enough, we have a what? This is geometric. So you have this geometric series. You go, all right, geometric. Now, R, the absolute value of R is smaller than 1, isn't it? So what is your sum going to be? S, A over 1 minus R. Do you guys happen to know what A is? What's A? 0.3? And what's R? 1/10? Okay, let's see what this is. So this is 3/10 over 1 minus 1/10. Is that 9/10? So this will be 3/10 divided by 9/10, which is 3/10 times 10 over 9, 3/9. What's our sum? Our sum's 1/3. So you might say, what does that even mean? That means the decimal representation here is 1/3. I'm sorry. The fraction representation here is 1/3. This is what you guys are showing. That's 1/3. So if I go to the TI, sure enough, if I write 1 divided by 3, what do you guys get? Isn't that 3 repeated forever? Sure enough. So this is like saying, if you guys want to know what this is, you're looking at really part of the definition of a rational number fraction. Rational number is any number that can be written as a decimal that's called terminating. It ends. The decimals terminate. Like, for example, 1/2, right? You say, what's another? This is part of the definition of being a fraction, 1/2. That's terminating. 1/3 is non-terminating. But if it's non-terminating and there's a pattern, we call that actually a rational number. A fraction. Those are rational numbers. So any fraction, if I put 7 divided by 8, ladies and gentlemen, well, that's terminating. I can even say 9 divided by 8. Well, that's terminating. How about 12 divided by 7? Well, believe it or not, that's non-terminating, but there's a pattern of digits that you see. Okay, you can put 2 divided by 3 here. Again, non-terminating, but there's a pattern there. It's really 0.6 with the line. This approximates. Okay, T approximates. So you're really looking at geometric series. They're all can be written as a fraction, in case you guys didn't know. Okay. Now, I want to introduce you guys to another idea that's going to be extremely important here. I'm going to write it down this way. We don't only deal with geometric series. Okay, there's a very classical example here of this. So they're going to say, show that this series is less than infinity. This is another way of saying, right here, this expression is another way of saying converges. Okay, being less than infinity means you're finite. So they want you to show that this thing is finite. Show the convergence. They could use the phrase convergence, or they could put less than infinity. Okay, so that's kind of what the idea is. Now, if you look at the terms, right, you say, isn't this 1 over, these are the terms. N is 1. Now what happens when N is 2? Now what happens when N is 3, right? That goes on forever. So we get 1/2 plus 1 what? 6 plus 1/12, and this goes on forever. So what we've been trying to do is we've been trying to say, hey, maybe these are geometric, right? AR squared. So let's try to go through this, and it might be geometric. So this information says that A is 1/2, AR is 1/6, 1/2 R is 1/6. What does that mean about R then? R is 1/3. So that AR squared is 1/2 1/3 squared, which will be 1/2 times 1/9, which is 1 over 18. Is this geometric? What are you supposed to get for AR squared? You're supposed to get what? You're supposed to get 1/12, ladies and gentlemen. That's not what you're getting. So this is not geometric. So since this is not geometric, then what do? You're going to have to do the following. We're going to have to consider the sequence of partial sums. Okay, so this is kind of like I said, we're trying to do a transition here from you. We're going from the geometric series situation to, in general, you don't always have a geometric series. So how we find convergence or divergence, we're now moving on, meaning it's not as simple. But this example is a very good example of what we call, this is going to be what's known as a telescoping series. Okay, now you go, what do you mean it's telescoping? What's the sequence of partial sums? You guys remember that? Sn, that's the first n terms, is the sum. I'm going to have to change my index. I goes to 1 to n, 1 over I plus 1. You see, this is what they're saying. you're going to end at n. That's the first n terms. That's the sum of the first n terms. This is the sequence of partial sums. The very famous sequence of partial sums. We're going to have to go back and use the definition. So this is code for saying go back and use your definition of what it means for a series to converge. Now, let's look at the terms. You say this is going to be 1 over 1 times 2. 1 over 2 times 3. 1 over 3 times 4. Okay, now this is not going on forever. This ends at 1 over n plus 1. So you guys remember how these really work? This is where n is 1. This is where n is 2. N is 3. And this is just where n is n. This is for n. And I got to go back. Let me actually be specific. It's not, this is where I. That's your index. This is called the index. Okay, so we're plugging in the values for what? For I here. This is important. Plugging in those values for I, and then we end at n. And you say, okay, well, that's what this thing looks like. Okay, however, go back over here. Here's what I want you guys to do here. Let me get another color, I guess. You see this right here? Isn't it true that I can write the same exact terms? See that there? 1 over I plus 1. Do you guys know what that equals? That's 1 over I minus 1 over I plus 1. You might say, how do we know this? Do you guys know how we know this? By what? Partial fraction what? Yep. You guys ever take that before in your life? You ever study partial fraction decomposition? You go, no, Mr. Judge, I just jumped into this course because I don't know what my counselor told me. Just take it. Taking those courses will just waste time. Anyway, you say, no, I had Snodgrass. What does Snodgrass do? I don't know what Snodgrass did. So we use partial fraction decomposition. Now, let's go back to what this means. Remember what that means here. I can replace that information with what you guys see here. Now let's look at the terms, okay? Notice what my terms are going to be for this sequence of partial sums. This is 1 minus 1/2 plus. Now this happens with I being 1. Is that true? I'm going to plug it in. Now I'm going to plug in I being 2. You go, okay, what does that give me? It's going to give me what? 1/2 minus 1/3. Okay. Now what's the next term? That happens when I is what? 3. So what do you guys get? 1/3 plus, no, I'm sorry, not plus, minus. It's a difference. Minus 1/4. Now you're going to keep going. 1/4 minus what? 1/5. Is that true? And that's going to keep going all the way up to what? 1 over n plus 1 over n plus 1 now. So let's write down what I is, because I think that's important to keep track of the index value. And this will be I equals what? N. This is your sequence of partial sums. This is at Sn. So, do you guys know what's going on here with this? What's what's this? What's canceling? This. Is that gone? And this cancellation. What's going on here? Yeah, what's going on? You want to know something? Let me let you in on a little secret. Sometimes it's hard to see what's really happening, isn't it? So if I said to you guys, if I look at just two terms, right? The first two terms looks like the second value and the first value go away right in here. And then what happens again? That second value and the first value go away. Then what happens again? That second value and the first value go away. You okay with that? And then you say, well, what is left? I'm not quite sure what's left, because you want to know what I have to do? I'm going to go to the prior term. Okay? You say, what's the prior term? I'm going to look at this situation here for the prior. This is n minus 1. So when n minus 1 is, what do we have? We have what? I think it's 1 over n minus 1 plus 1 over what? N. Okay? And that's minus, not plus again. So what's the pattern again? The second term, I want to use the same gray. And that first term cancel. Is that right? You guys with me on that? But what about this n minus 1? Well, all these terms are going to cancel. They are collapsing. They're collapsing. So what you end up getting here for Sn is something very, very nice. You get 1 because all the other terms collapsed. And I think I did another typo. I want to say this is a minus. This is what you end up with. All the other terms have collapsed. But you should be happy here, ladies and gentlemen. All the terms collapse. This is called telescoping. I can now take the limit of Sn as n goes to infinity. That limit, ladies and gentlemen, is 1 minus 1 over n plus 1. Do you guys know what that limit is? It's 1. We get a very nice closed form for the sequence of partial sums here. And now that limit is 1. That's a finite value. Isn't that finite? That's the S value. You say, what did you just show? We showed that the sequence of partial sums converges. Therefore, the series what? Converges. Where is it? Yeah, there we go. We just showed that the series converges. Right in here. In fact, we know something more than that. Okay? We know this is what this means here. We actually found the sum. Generally speaking, you can't really do that very easily at all. In the beginning, we can. By using the definition here of that sequence of partial sums, this right in here is the sum, ladies and gentlemen. It's 1. So in the beginning, it's easy to do, but generally speaking, it's not so easy. Just to kind of let you guys know, it's generally not an easy thing to do.
first one, the n was not infinity, and then we changed it into infinity. It's from general to the
Well, remember what this is. Remember the sequence? S1, S2. This is the sum of the first n terms. But this is the sum of all. This is now, you don't have just n terms. You have more than n. That goes on forever. But if you can show that Sn goes to S as n goes to infinity, then that means, again, that this thing equals S. It's finite. So what we did is we took the sequence of partial sums called Sn. That's the sum of the first n terms. Okay, so this is just the sum, Sn. This gives you the sum of the first n terms. So if I told you know what, if n is 10, you know what I mean? Then what is S10? It's 1 minus 1 over 11. And that's going to be, S10 will be 10 over 11. But that's a finite sum. That's the sum of the first 10 terms. Now let this n go where? To infinity. Let that n value get arbitrarily large. In that case, if it goes to a finite number, like in this case S, that's the sum. That's the definition of a series converging. Very difficult to do in general. Very difficult. See, in this section 12.2, they show you, hey, guess what? They show you, ladies and gentlemen, that some of these things converge by definition. So in the beginning, in this section, you'll see some, like the geometric series will converge because we proved it using the sequence of partial sums. But what's under the hood always is that sequence of partial sums needs to converge for you to have a finite series, meaning it adds up to an infinite sum adds up to a finite value. One is finite. But you got to get a handle on that sequence of partial sums. That's the key. Very difficult to do in general for just any arbitrary series. But in the beginning, it happens. Now, I'm going to give you guys the definition here, another definition of something here. We're not going to prove this one today. But we have a very, very famous series called the harmonic series. Now you say, what are the terms of the harmonic series? It's 1 plus 1/2 plus 1/3, okay? That's your harmonic series. Now I'm going to give you guys a fact. I won't prove this today. I'll prove it in the future. I think your book proves it. The harmonic series, I'm going to give you guys some notation, equals infinity. What does this mean to say it equals infinity? This is another way of saying that the harmonic series diverges. Okay? And this is a very, very famous series, but it's a famous divergent series. It's not geometric. If you try to use the geometric formula, you're going to find it's not even a geometric series. So we've transitioned away from geometric. Don't think everything in the world is geometric. No, not everything in the world is geometric. Here's an example of a very simple series, and it's called the harmonic series, and it diverges. Your book gives a proof, but I don't do it in this section in 12.2. I prove it later. Now, I'm going to write that down in our notes. Proof when? Later. Okay. We'll come back. We'll prove that. But I want to give you guys an important fact, an important theorem here that we're going to be using in this course. Probably one of the most important facts in this section. And this is the statement. If a series is convergent, then the limit of an equals 0. That's not the limit of Sn, so be careful. This is the limit of an. This is a fact. Okay? I want you guys to see that. Now, I'm going to prove that for you guys. So here's the proof. We assume that the sum of this series an is less than infinity. Okay, that's just another way of saying that this thing what? Converges. So we assume we have a convergent series. Now, what does that mean? Well, we're going to take a look now. What that means is we're going to consider the sequence of partial sums. And what do we know about that sequence? Sn is a1 plus a2 all the way up to an, okay? And that's the sequence of partial sums. So I should say consider that sequence of partial sums, really, not let, but your book might use the word let. It's better to just say consider this. I'm going to do a little bit of algebra. Then this implies that an, ladies and gentlemen, is Sn minus a1 minus a2 all the way up to minus an minus 1. And I want you guys to focus on what the meaning of this is. You say, what is this? Well, that's the sum of the first n minus 1 terms. So this is Sn minus 1. So what I'm saying is an is Sn minus Sn minus 1. You get that an. Now, if we take the limit of both sides here, on the right side, I get the limit of a difference. Sn minus the limit as n goes to infinity, Sn minus 1. I know that this is S, and I know that this is S. You say, why? Because the original series converges. That means, this is our assumption, right? We assume the series converges, which means the limit of the sequence of partial sums is S. That's S. This is what it means here automatically. Right? This means Sn goes to S as n goes to infinity because we have convergence. And this is going to be the difference now equal to 0. So what we showed is the conclusion that the limit as n goes to infinity of an equals 0. And that's the end of the proof here. Okay, so I want you guys to really understand this statement here. We just showed that this thing is what? Valid. Okay? This is valid. However, you got to be very careful with these kind of statements here, okay? I'm going to go back and talk about math. Everybody hates that. Do you guys know what this statement is here? This is called a conditional. That conditional is equivalent to the negation of Q implying the negation of P. This is the contrapositive. Okay? Now, why do you care about that? Well, when you show a conditional is valid, you get the equivalent statement, the contrapositive is also valid. This is going to be a very big deal for us and a very powerful statement. The contrapositive, ladies and gentlemen. Now, you say, what is this? I have to negate the P. I have to negate. This here is what we're going to negate here. Right? This is my, if I can get this, I'm going to be cut. This is my P, and then this is my Q. I'm going to negate Q. This is a very big deal. So if the limit of AN equals 0, the negation of that is this statement here. If the limit of AN is not 0, or the limit of AN does not exist, because that's the exact opposite of the statement. Your book writes it this way: R does not exist. Okay. Then when we know that is valid because it's the contrapositive, I can now negate P. Negating P is the opposite of convergence. What's the opposite of convergence? Divergence. Then this means, ladies and gentlemen, your series AN equals infinity, which is another way of saying what? Divergence. Now, why do I care about this? You see, I really care about this statement. This is the useful statement right in here. That is useful. It is so useful. You know what we call this statement? This is known as the test for what? Divergence. This is called the divergence test. And this is probably in some ways the most important. I would say there's two important ideas in this section. One is the definition of that of the sequence of partial sums. Your sequence of partial sums converges, then the series converges. This is the second most important fact from this section 12.2. And there's a lot of power in this. We're going to use language and logic. I got to focus on that part of it, because this is really the meat of some of these questions. This is a very important thing. This is called the test for divergence. You say, why is it a test? Because if you can show that the limit of what? That AN term. Where does that AN term come from? It comes from a series. This is what? That's where it comes from. If we can show that the limit of AN is not 0, then we know that the series diverges. We can guarantee the series diverges. So that's all I have to show. What if I show that the limit does not exist? Well, then I can guarantee that the series what? Diverges. This is called the test for divergence. Remember, this chapter is going to be all about tests, various tests. And that comes from the fact I just what? Proved. So I proved a conditional, P arrow Q. This is valid. P arrow Q, that conditional is valid. So this statement I just showed you guys, in some ways, that's kind of like it's directly and it's meaningless. Directly, it's meaningless. It's meaningless directly. But the contrapositive is not. This is extremely useful. And so we get the contrapositive statement free of charge, and this is known as our test for divergence. We just have to show now that the limit of AN is not 0 or does not exist. If we can do that, well, guess what? We can say that the series diverges. Guaranteed to diverge. Nothing more than that. And so, ladies and gentlemen, that's where we're at. We're going to have to look at some examples of that very, very famous theorem. I could give you a quick example. You guys want to see a quick example? As a little teaser. Here's a quick example. You guys see this here? That's my AN. Okay? What do you guys know about the limit of that AN? What's this limit equal to? Not limit 1/2? Do you guys see what I'm saying? Guess what? That's not equal to what? 0. So what happens if the limit of an in your series is not 0? What could you guarantee? Diverges. So here's what you essentially say, ladies and gentlemen. This series what? Diverges by the what? Test for divergence. It's an extremely powerful test. That is gold. Gold. And we're still not done with the what? Section, ladies and gentlemen. You go, Mr. Judge, you're not done with that section. No, I told you guys. 12.1 and 12.2 is the foundation. And without the foundation, it does everything we do doesn't mean anything to you. So there are students out here who are, I hate to say it, they're not doing any of the sequence and series stuff. They're still learning how to integrate and differentiate. And we're going to be diving into these ideas. They're very simple, but you do got to keep up with them. They can be very simple. They could also be very difficult. Some of these questions could be extremely difficult. Like if you look at your book, I can spend a whole month on one section. I could spend a whole month on one section for every one of these sections. But we can't do that. But anyway, what you guys have done, you've seen an example of the test for divergence and why you care. And we're gonna do some more tomorrow, and we're gonna continue. So I'll see you guys later. Have a great day. Stay safe. Your homework is in Canvas, and take care. And see you guys later. Done yesterday and today. I'm gonna go back to a few of those ideas. Okay. So I'm going to go back to that idea of a telescoping series for you. And I want you guys to show that this series here converges. So this is kind of another example here. 2 over n squared plus 4n plus 3 converges here. So I'm going to give you guys a hint that this thing is actually what? Telescoping. Okay, but here's another hint. We're going to do a little bit of algebra here. That algebra here is going to be, ladies and gentlemen, right up here, you're going to use partial fraction decomposition here. Okay? Because that's going to be an important difference, because telescoping means collapsing, and you want terms to collapse. They could never collapse if there is no difference. So to remark to you guys that this portion there is going to be 1 over n plus 1 minus 1 over n plus 3 here. Okay? So really, you're going to really show that this series is the same by partial fraction decomposition. Okay? So I'm going to give you guys some time here to do that, but let me help you guys get started on this. Let's look at the terms of the series. Remember, telescoping means it's collapsing. Terms are going to collapse. Okay? So we're going to say terms here will collapse. And how they collapse is really based on the fact that there's going to be some subtraction of terms. Okay, that's just because you have subtraction there doesn't mean everything collapses, but these are specially chosen questions, so that does happen. And then you might say, okay, well, how do we really look at this? Well, let's start to look at some of these terms here. We're going to have to really eventually look at the sequence of partial sums. So we're gonna see what happens here. So I want you guys to note, first of all, this was not geometric. It's not a geometric series, so we're going to have to consider the sequence of partial sums. Okay. Anyway, good morning to all of you there. So consider the sequence of partial sums. So what that's going to mean is this. We're going to have to say, okay, Sn, okay, your sequence of partial sums. Or Sn, Sk, whatever you want to do here. All right, so maybe we're going to say we'll let Sn be the summation of I goes from 1 to n, 1 over I plus 1 minus 1 over I plus 3 here. Okay? So we're going to see the terms now. So this is what we have to consider here because it's not geometric. Okay? They want us to show that this thing converges. We can't use that rule, the test for divergence at all. Okay, because it doesn't diverge. This thing converges. So don't say, can I go back to the test for divergence? No. This is a test for divergence. If you looked at the limit here, okay, just to kind of put everything here together for you. They're wanting you to show that this thing, first of all, converges. So if you said, okay, I want to just look at this AN, and you say, Mr. Judge, the limit of AN equals 0 here, right? Because you're looking at the limit of that 2 over n squared plus 4n plus 3, that is 0. Yes, that's 0. Okay. But what does that mean? That doesn't mean anything. What means something is if the limit is not 0, or if it does not exist, then we can say that the series diverges. But the fact that this limit equals 0 has no meaning. So I want you guys to note that as well. I'm just going to say to you guys, note anytime the limit of AN equals 0, if you have that, then the series can be convergent or divergent. You don't know. There's no guarantee of what this will be. Okay? So that's an important detail. A lot of times people say, hey, the limit of AN is 0, therefore it converges. No, not at all. Okay? Not at all. The test for divergence says that the limit is not 0 or does not exist, then we can say divergence. That's a guarantee. There's no test for convergence on these series in general. There's going to be a lot of tests in our future, but there is no general test. There's a general test for divergence. So I just want to kind of throw that out there for you guys here because sometimes people say, but you told me if it converges, then the limit is 0. Well, that's backwards. That's a backward statement. So I'm going to revisit this stuff again, but I just want to kind of throw that out there that if it converges, then AN is 0, but it doesn't work the other way around. Okay, the converse statement is not valid. That's what I'm saying here. Say, what's the converse statement? This statement here is invalid, the converse. Don't read it backwards, but I'll revisit that. Anyway, I just want to point that out as we started this adventure in showing the telescoping series converges by partial fraction decomposition. We get our start. And then we consider, again, the sequence of partial sums. Anyway, just want to let you guys know. Okay, let's continue. All right, so we say, okay, let's just continue with this. All right, well, what does that mean? What are the terms? What's the first n terms? Well, when I is 1, don't we get what? What happens when I is 1? We get 1/2, ladies and gentlemen, minus 1/4. That happens when I is 1 because we change the index here. Now plus, what happens when I is 2 now, right? We get, okay, 1/3 plus 1/5. If you guys notice that. All right. Now I is 3. What do we get when I is 3? Plug in the values there. We get 1/4. And that's, sorry, let me go back here. It's minus. That's minus 1/6. And then we get 1/5 minus what? 1/7. That happens when I is 4. So notice what's going on with the terms, ladies and gentlemen. Okay? We're going to have to look at this. I is 1, I is 2, I is 3, I is 4. Look at all these terms. Excuse me. 1/6 minus what? 1/7. I is 5. Now, generally speaking, this pattern continues all the way up to what? When I is n here, okay? And you go, well, what's that going to be? Well, 1 over n looks like, right? Oh, n plus 1, I apologize. Minus 1 over n plus 3. So this is what our sequence of partial sums looks like. Remember, we want a closed form. Some of these terms are going to collapse, right? So you can get rid of your parentheses if you need to. Or you can keep them, doesn't matter. What I want to say is some of these terms will collapse. Now, what terms collapse? When do you start seeing things collapse? Here. Okay, because this is a telescoping series. And you might say, okay, we got 1/4. Well, look at this. With the first term, the second term, what? Goes away. And then on the third term, the first term goes away. Now I'm going to change my color maybe. Maybe that helps. I don't know. Okay, so guys, you see the plus and the minus going away? This is collapsing. Now you got plus 1/3 minus 1/5. The second term goes away. And then how many terms later? 2 terms later, again, that first term goes away. And what is present still is the 1/2, the 1/3. Okay. Now I'm going to change my color again. Let's go to the next one. Right? We can notice now, oh, what's going away now? We see a 1/6. The second term go away, and then 2 terms later, the first term goes away. All right, you guys see what I'm saying here? Because the plus and minus, some of these terms are going to collapse. So you guys want to try that here. Now, I'm going to go back and I'm going to do some more here, so you guys can start to see what I'm saying here, because you want to see that pattern. So when I is 6 now, we go, oh, that's going to be what? When I is 6, what do we get? Something's wrong here on this. This is minus 1/8. Sorry. Okay. So then what do we have now? You got what? I plus 1. So this would be 7 minus, and then this is I plus 3. So this is minus 9. So you might say, what's going on with this? I is 7. This would be 8 minus 1 over, looks like it's 10. Okay? So I want you guys to see what's happening now again here. You got 4, 6, 5, 7, 2, 4. All right, let's double check here. We okay? Okay. Again, let's change the color. Second term, and then 2 terms later, the first term goes away. So what I'm going to now do is this. I'm going to go do the following in case you guys don't know here. Can start to see what's happening here. The second term goes away, and then 2 terms later, the first term goes away. Okay? Second term goes away. See the colors here in red? Look at the red. Second term goes away. 2 terms later, first term goes away. Look at the next one. Second term goes away. 2 terms later in purple, the first term goes away. Orange. Second term goes away. 2 terms later, the first term goes away. That pattern continues. So it looks like it's going to continue. So what I'm going to do now is this. I'm going to now check this from I being what? Not n. I'm going to do n minus 2. And then I'm going to check I is n minus 1. Then I'm going to check here I is n. Okay, we're going to finish it off at n again. So when I is n minus 2, 2 terms prior, we plug in n minus 2 here. It looks like we're going to get n minus 1. Minus 1 over, plug in the n minus 2 over here. That'll be n plus 1. I is n minus 1 now. Go, oh, n minus 1 plus 1. Well, that's just an n. And plug in the n minus 1 now for both. So that goes n plus 2. And then finally, you get 1 over n plus 1 minus 1 over n plus 3 when I is n. This is a sequence of the first n terms. But let's pay attention to what is collapsing, what is going away here. And I want to get some other colors. Maybe orange, I don't know. Or which ones have we not used? We use orange, green, purple, red. Maybe gray. Gray, the second term again, and the first term 2 terms later. Okay, now remember what's going on with everything else in the middle here. These are going to go away too. All of this stuff is going away. But we want to find out, what are we really left with here at the very end here? Okay. So it looks like what we're left with is that very last term. Okay. And then you might want to see, well, what happened with, if we had I being 3 terms prior, right? So 3 terms prior, you get 1 over n minus 2 plus 1 over, it looks like it's n, if that's n minus 3 plus 3, yes. So here's kind of what I want you guys to see here. Okay, what's going to end up going away is this, the first term, or the second term of the first series there, 2 terms later, this goes away. In fact, all of these other terms are going away. And really what you really end up with is these terms, all in gray. Everything else collapses. Everything else goes away. So then you get the closed form of your sequence of partial sums being 1/2 plus 1/3 minus 1 over n plus 2 minus 1 over n plus 3. Because everything in gray is really what's left over now. So we're going to kind of review. Okay, you're going to review all of that. This is the closed form. We're reviewing the telescoping series because there's some nice questions there. So the limit of Sn, as n gets big, is that limit, again, of everything we just seen. 1/2 plus 1/3 minus 1 over n plus 2 minus 1 over n plus 3. And then that limit's going to be 1/2 plus 1/3. And if you do your arithmetic, that's a finite number, 5, 6. So the sequence of partial sums converges to 5, 6. So if you guys remember what that means here, right? When the limit of the sequence of partial sums is finite, that's the sum. So this is what it means to say that this series converges to that 5, 6. So ladies and gentlemen, this equals 5, 6. It's not geometric. We didn't verify that, but we just shared with you guys here that this is what? 5, 6. That is less than infinity. That is finite. That's what we just found. And that's showing convergence here. And that's the idea. So, I want to revisit this concept of telescoping series because it's a really, really big deal. Because there are some series that telescope, they collapse. Okay? All right. Just going to keep an eye on the chat. Okay? So now here we go. I want you guys to know, I'm going to go back to this statement here again to go back and remind you guys about the logic. Okay? Go back to this statement that we proved last time. I have this statement. If a series converges, we know that if it converges, then what's the deal? We can conclude that the limit of an is 0. So the last example was a convergent series. 2 over n squared plus 4n plus 3. We know this converges. We proved that. What that means is the limit of an equals 0. Because we had convergence here, right in here. But I want to remind you guys, this statement directly means nothing. Just because you can see that, let me rephrase that. This is a problem here. And I want to find maybe pink. Well, no, yeah. This here is the problem that exists. Okay? Sometimes people think if the limit of an is 0, then that means we have convergence. No, it doesn't. This is not valid. Okay? This conditional is written as P arrow Q. This pink conditional is reading it backwards. You don't want to read it backwards. This is Q arrow P. This is called the converse statement of a conditional. Converses aren't generally, if a conditional is valid, converses aren't valid by default. You got to prove that. And in this case, it's not the case. This is an invalid statement. But for every conditional that's valid, the contrapositive statement is valid. And this is where we get this test for divergence. It's the contrapositive statement. Right? This is the gold here. Okay, so this is the gold. This is the contrapositive. And if I can move that there, that is saying for a series, if the limit is not 0, we have to take the negation, or does not exist, then the series diverges. And this is called the test for divergence. It's the contrapositive statement. That's the gold. And I'll give you another example of a telescoping series. Okay. And this time they're going to say what? Show that this series here diverges. Okay. Now, sometimes people say, okay, here's AN, right? You say, Mr. Judge, if the limit of AN equals 0, then what does that mean? That means nothing. It's inconclusive. The series can converge, or the series can what? Diverge. Okay, this is in an inconclusive situation. Because again, in this case, the limit of AN is 0, right? So you might say, like in this example, the limit of AN, here's my AN, is 0, but the series converged. In this example, the limit of AN is also 0. You go, but what's going on? The limit of the natural log of 1 plus 1 over n as n goes to infinity, this is the natural log of 1. This is 0. Okay, so what happens when the limit is 0? Nothing. The series can either converge or the series can diverge. It's an inconclusive situation. So I want to make clear that just because you have that limit AN being 0, it doesn't mean anything. Okay? And in fact, this case, this telescoping series diverges. Now, you say, how do we show that? Consider the what? Sequence of what? Partial sums. Say, well, how do I do that? Well, Sn is the sum. I'm going to change the index again from I to n, make it a finite, and that's natural log of 1 plus 1 over I now. All right, you guys okay with that? Okay. So what is this? Well, let's try it out again. Let's see. What is that going to be? Aren't I supposed to have some differences if this is a telescoping series? Where are my differences? it's a telescoping series. I got to write out some differences there because I need these terms to collapse. This is not geometric. I don't have to go and prove that to you guys. This isn't geometric. So you might say, where do I get the differences so they can have collapsing? Well, let's do some arithmetic. Can I replace that 1 with I? Do you guys know what I mean? So that's I plus 1 over I. Natural log of I plus 1 minus the natural log of what? I. So this is by properties of, it's called the quotient rule. Right? It's a quotient rule. So Sn is the sum from 1 to n. Natural log I plus 1 minus natural log of I. Now I got some differences. Because without any differences, there's no collapsing. You got to get rid of those terms. So Sn will now be, let's look at the terms here, right? Let's say, okay, start with 1. Well, natural log of what? 2 minus natural log of what? 1, okay? Plus, well, what's the next term? I is 2. Natural log of what? 3 minus natural log of 2. This happens when I is 2. Natural log of, what comes next? I is what? 3. Isn't that natural log of 4 minus natural log of 3? Is that true? Now let's look at the next term. I is what? 5. We get natural log of 5 minus natural log of, what is that? I'm sorry, 6 minus 5. So far, so good. And so this is going to continue all the way up to, let's say, what happens when I is n minus 1? Well, then we get the prior term, that's natural log of n minus 1. So n minus 1 plus 1, that's n, right? Minus natural log of n minus 1. And then plus natural log of n plus 1 minus natural log of what? N. Happens when I is n now. So we're going to plug in all of those index values here, right? I is 1. What do we get? I is 2. I is 3. I is 4. And then n minus 1 all the way up to n. Now let's see what collapses. You guys see anything collapsing? Let's see if we can make some sense. See what subtracts. When I is 1, the first portion goes away. And then what? This ln 2 minus ln, we got ln 2 minus ln 2. The first term when I is 1 and the second term when I is 2. And then again, the first term and then the second term. And this is a typo. This should be what? This should be 4. When I is, what do we have here? When I is 3. 3 plus 1, isn't that 4? Okay. When that's what happened. We didn't put I is 4. We went to I is 5. So I said, wait a minute, something's wrong. I'm drinking my coffee, ladies and gentlemen. I left my coffee at home. So I'm a mess. Sorry about that. Okay, let's continue. The first term when I is 3 and the second term when I is what? The next term. So things are going away, and then you say, well, what about how do they end? Right? How do they end? The what? What is this? The first term and then the what? The last term. And so the sequence of partial sums now, if you look at what's going on in terms of two terms here. Everything in the middle is what? This is gone. This is gone. If you look at I as n minus 2. So what you have left, ladies and gentlemen, is this first term to begin with, right? And then you're finally left with this last term. But what do you know about the first term? What's natural log of 1? This thing's what? That's 0. So here's my point. The sequence of partial sums is really natural log of n plus 1 here. Because everything else collapsed. Everything went away. That subtraction is what makes things collapse. And it's subtraction between adjacent terms. Even though that's not what you started with, but you used some algebra. And so what do we know about this limit, right? You can say the limit here as n goes to infinity of Sn is the limit as n goes to infinity of natural log of n plus 1. This thing equals infinity. Okay? This is what we mean by what? What's the story? The sequence of partial sums diverges. So Sn goes to infinity as n goes to infinity. That means the series diverges. Okay? Your series, ladies and gentlemen, this is the format of it. And that's really the proof behind this. But there's a couple of overlapping ideas I want you guys to be aware of. Extremely important overlapping concepts. That the test for divergence, ladies and gentlemen, that big test is really what's happened, is not applied here. We can't apply it. Okay? The test for divergence, we can guarantee divergence when the limit of an is not 0. But if the limit of an is 0, we cannot guarantee convergence or divergence. There's no guarantee. Okay, let me say that again. If the limit of an is 0, there's no guarantee about convergence or divergence. We've seen 2 examples there already. We can only guarantee divergence if the limit is not 0 or does not exist for this situation. Right? And now you might say, can I see another example of that? Because, I thought I understood it, but maybe not. Okay, well, here's an example. They can say, show the series natural log n over 2n plus 5. What is this? Diverges. Okay. Is this geometric, by the way, ladies and gentlemen? Would you say this is geometric? No. How do you know? You can test it. But it's not even in the format of being geometric. Is that right? What's the format of a geometric series? Doesn't look like that, does it? You got a natural log. You don't have... It's not geometric. Okay. What's your AN? What do you guys know about this limit? What's the limit of AN? What's that limit? What do you guys think? What's going on here? You guys know what this limit is? You wouldn't know what this limit is. Well, if you said, I'm going to go out to what? First of all, you need to note that you have to take, where does n over 2n plus 5 go to as n gets big? Does that go to 0? Or does it go to 1/2? Right? If you use calculus 1 and you said, hey, this is from calculus 1, I think when we're doing calculus, I go to purple. Okay, by calculus 1, what's this? Limit x goes to infinity. X over 2x plus 5. I mean, I could actually use calculus 2. Infinity over infinity. What's this? L'Hopital's rule. Derivative of x is 1. Derivative of 2x plus 5 is 2. Limit of a constant, isn't that 1/2? So this is by calculus 2. And then what do we know about the natural log? That's a nice continuous function. So that means the natural log now of n over 2n plus 5 goes to, because natural log is continuous, 1/2 as what? N goes to infinity. What do you guys know about this? Natural log of 1/2. Do you guys know what you just showed? You showed the limit of an equals the natural log of 1/2, and that limit is not 0. What does that mean if the limit of an is not 0? Do you guys know what that means? Where is it? If the limit of an is not 0, then what can we conclude? Your series what? Diverges. Don't be so eager to jump to the limit of an equals 0 and you think you have a conclusion. You don't. Limit of an equals 0 is inconclusive, but the limit of an not 0 is conclusive. That means your series diverges. Whatever that series was. And the an, you guys know what an is. This is the an we're talking about right here. So you just showed that the series diverges, ladies and gentlemen. And that's what they want you to do. They want you to show that here. Show this series diverges. It does, and what you should say is it diverges by the what? This is what you want to say. By the divergence test. Or by the test for divergence. Anyway, so we can do some backtrack on some special geometric what? Series. they'll say the following. For what x do you have convergence? X minus 3 to the nth power. Now, these are geometric series, believe it or not. You might say, really? Yeah, they're geometric. So like I said, I'm going to do a little bit of backtracking on this for you guys. Let's look at the terms, right? You say, what are my terms? Well, this is going to equal x minus 3 to the first power plus what? X minus 3 squared plus x minus 3 to the third forever. Remember, what does that mean? A is x minus 3. What's AR? X minus 3 squared. Is that true? Do you guys remember this kind of, what does that mean about AR squared then? Because we have to check AR squared, don't we? So what is AR squared? X minus 3. X minus 3 squared. Is that x minus 3 to the third? It sure is. Doesn't it check out? Okay, when do you have convergence? If the absolute value of r, what is r going to be? Do you guys know what r is? If a is x minus 3, what is r going to be? Do you guys know? Because that means x minus 3 times r is x minus 3 to the second power. So what is r? If you say x minus 3 squared over x minus 3, what does r give you? X minus 3. This is my r, ladies and gentlemen. So we just found what r is. I'm going to use red. I like using red for r. So you're going to get that r value, okay? And then not only do you get the r value, you're going to get what? What does that mean? That's -1 less than x minus 3 less than +1. And so you have an absolute value inequality. If I add 3 to the left, the right, and the middle, I get 2 less than x less than 4. So these are the values of x where you have what? Convergence for these special geometric series. Okay, so these are kind of another example of something like this would be, what if they gave you x plus 3 to the n over 2 to the n is 1 to infinity. That's also geometric. Okay, now you might say, well, why would that be geometric? Well, this actually simplifies to x plus 3 over 2 to the n. Okay, just using a little bit of algebra. So what are the terms? Okay, you get x plus 3 over 2 to the first, x plus 3 over 2 squared, x plus 3 over 2 cubed. And then that goes on what? Forever. Geometric. A AR squared, AR cubed. Okay. So what's the deal? This is geometric. Do you guys happen to know what R is? What's R here? If we can say A is the x plus 3 over 2, right? What's your R value in this geometric series? Oops. It's R. R squared. Looks like my powers are... Isn't R also x plus 3 over 2? This is a geometric series. Okay, you guys understand what I'm saying? How do we know that's the case? If AR is what? What does that mean about R? So if the absolute value of R, the absolute value of x plus 3 over 2 is less than 1, what does that mean? We have convergence. So if you guys remember from pre-calculus, okay, this is a what? What does this mean, right? You can take properties of absolute value. You know the absolute value of 2 is 2. You can multiply both sides by that positive number of a 2 by pre-calculus. Ladies and gentlemen, this is an absolute value inequality. What does this mean? Negative 2 less than x plus 3 less than positive 2. Subtract 3, subtract 3, subtract 3. Negative 5 less than x less than negative 1. So they want to know the values of x for which you have convergence here. These are some geometric series. At least in these examples here. Now, this is another geometric series, ladies and gentlemen. Believe it or not. Sine of 1 to the nth power. Okay, now this is not degrees. This is in radians here. Okay, so if you look at the terms, this is really sine to the first power plus sine squared to the first power plus, just keep raising those powers here forever. Okay, so this is your A. This is AR squared. Yes. What do you mean? It's okay. They just want to know the values of x for which you get convergence here for these. And, you know, we revisit this at the end of the section because these are what's called power series. So we revisit this. They just introduced them to you now as geometric series, which is good. I like that idea. But this portion here, I'm going back to regroup about telescoping series, your test for divergence, geometric series. Just going back to regroup some of these here. Here's the deal. Does this series converge, right? And the answer is yes, because it's geometric. Your A is sine of 1. AR is sine squared of 1. What does that mean R has to be? R is the same as sine of 1. Okay? And so if you have the absolute value of sine of 1, which is R being less than 1, you have convergence. Now, what is sine of 1? If I go to my TI here, right? Sine of 1, what's that going to be? This is in, I got to make sure my mode is what? In radian measure. All this is in radians. So I'm going to hit radian. Sine of a radian value, sine of 1 is what number? 0.84. What's my point? You guys know what the point I'm trying to make? Sure enough, this is smaller than 1. So we have what? Convergence. Okay, so this is a geometric series that converges. Now, you might say, but Mr. Judge, you have not been putting what the sum is. Well, okay. What's this sum going to be then? The sum is going to be sine of 1 over 1 minus sine of 1. So even in my calculator, I can find out that infinite sum. I could just put sine of 1 divided by one minus sine of 1. And, you know, that's the infinite sum, by the way. It's about 5.30 what? 8. If I go out to the nearest thousands. So, you know, this is going to be the infinite sum for this geometric series here, by the way. So if you add up those terms forever, it's geometric, that's the sum. Because the absolute value of R is less than 1. That's the test for a geometric series for convergence. Okay, just so you guys know. But, you know, some of these others, like here, like I said, that we're revisiting, very popular. They can say, what about this? X plus 4 to the n. This is your geometric series as well. For what x do you have convergence? Okay, this is what x. Do you have convergence of these very special geometric series? Now, you can double check that they're geometric. AR squared. You could double check that. You will get that. Well, this is A going to be what? X plus 4. AR, by the way, is X plus 4 to the second power. What does that mean about your R? What does R have to be? R has to be what again? X plus 4. That's the R value. So if that's the case, what's the deal? If you have the absolute value of that expression there for R, if it's less than 1, you got convergence. Now, what does that mean? That means what? Right in here, right? What does that mean? That means -1 less than x plus 4 is less than +1. If you subtract 4 from the left, right, and the middle, the values of x for which you get convergence are between -5 and -3. So, you know, this is also, again, part of the, whatever you want to call it. This is part of the section here. All right, and I guess I just want to leave you guys today here with, you know, the very, very what? Just properties here of series. Okay? So you have these things called properties of series here. You got two convergent series and C is a constant. So here's kind of the first property. If you have C, a constant times that term, I can simply pull out the constant. That's all. And that can be proven. And that also, by the way, converges. And then if you have the sum of two series, well, since both of these converge, this sum converges. Because remember, converging just means a finite number, right? That means this sum you can think of as L, and this is M. So you got Cm. And then here you got L plus M. The third, AN minus BN. And that's L minus M. Okay, and then the very famous example that they have here, like in your book, they'll say determine if this series here, 5 over n, I believe it's n minus 1 plus, I think we did 1/2 to the n here. Right? Determine whether this thing what? Determine the sum. And all they want you to do is use properties. You say, what do you mean? 5 over n, n minus 1 plus the sum of what? 1/2 to the n. N is 1 to infinity. Pull out your constant 5. Now, what we showed earlier is what that sum is. And we showed earlier what that sum is because they both converged. And I don't remember what they were. I think the first one is 1. Is that right? And what was this 1/2 to the n? Do you guys remember? It should be in your notes somewhere. Did we do 1/2 to the n or 1/3 to the n? I think we did both. But the point of this is 5 times 1 plus what will be the answer? What do we get for 1/2 to the n? Do you guys remember? This is geometric. R is 1/2, and I think A is 1/2. So that sum is A over 1 minus R. So I think this is 1/2 over 1/2. Oh, that was also 1. So, okay, both of these were 1. So that means the sum will be 5 times 1 plus 1, which will be 6. So that's all they're asking you to do if you ever have to find this big what? This big series. You go, oh my God, that's a big hairy series. But no, they want you to go back and remember these properties, series properties. It's really a constant times that term. Pull out the constant. The sum of two terms, well, look at them separately and add. The difference, look at them separately and subtract. Anyway, ladies and gentlemen, welcome to the world of what? Series. So as you guys can see,